Good morning, everybody. Welcome to the next session of WOSMIP Remote. Our next speaker will be Anders Ringbom from FOI, who will speak about his take on xenon measurements. The floor is yours, Anders.
Thank you very much, Ted. Hello, everybody. So my name is Anders Ringbom. I'm speaking to you here from Uppsala in Sweden. And today I'm going to talk about mobile radioxenon measurements, the way they have been done so far, and I will talk about some new possibilities given recent technical development, which has to do with the ongoing radioxenon array project that we have been running at FY for several years now. Now, this is not a talk about arrays; it's about mobile measurements. But the array technique has some spin-off that I think can be used in this context as well. And I will talk about this in the WOSMIP context, that is understanding isotope production facilities and nuclear power plants. So why do we need and why do we do ground-based mobile measurements? Well, obvious reasons that we have been talking about for many years is to map the global background, of course, and find new release sources. But more specifically, you can also use these kind of measurements to, for instance, do an independent verification of stack measurements. There are some facilities today that have some stack monitors installed, for instance, in this stacks project. And they are measuring the radioxenon with a certain kind of equipment, germanium detectors and so on. And it might be very interesting also to measure the same gas outside, very close by the facility, using some mobile systems and try to compare the data. I think that would be an interesting comparison experiment to do. You can also, if you don't have a stack monitor installed in the plant, you can use this as an alternative to stack measurements. Say that you put your detector very close to the facility, you will have a strong signal and you will not be disturbed by other sources. And then you can do this as a kind of, I don't know what to call it, poor man's stack measurement or something like that. You can also use this to improve the atmospheric transport models, tuning the parameters in them. If you place several of them, several of these sensors out, with some distance, you can verify mesoscale models and whatnot. Another maybe more exotic thing is to perform plume hunting. That is, what I mean with that is that you can move the sampling point into the plume based on atmospheric transport forecast, for instance. And in that way, you can increase the detection probability and your signal. So this we actually did more than 10 years ago when we performed some mobile measurements outside Fleuris in Belgium, outside the facility there, isotope production facility. We got plume predictions every day from SEK SAM in Belgium, and we tried to move our sampler into the plume. And we were quite successful, at least some days, but it's not so easy. It's a laborious task to do. You can see some examples here on the screen where you have the plume, and then the yellow dot is the sampling point that we used that day. So the way we did it then, and the way mobile measurements can be done, is that we had a sampler on a truck. And in this case, we used the FOI mobile sampling system, which actually is more than just sampling. It's also pre-processing the sample into a transport column. And then this column is transported to a laboratory. In this case, we moved it to Sweden. So it's quite a long transport. And then we analyzed it and measured the activity. So this works, but it's a complicated process with a lot of logistics, and there are rooms for mistakes all over. So it could be done, but it's nothing that you can do like on a regular basis, I would say. So here I tried to categorize the main ways that one conducts mobile sampling measurements today. To the left is what I call field sampling. You sample your air either in a very simple way in a bag in a balloon or in a scuba bottle, for instance, or you can use a little bit more complicated process with some pre-processing. But then you transport your sample to the lab and you analyze it there. The other way to do it, and the way it's done today also in, for instance, the measurements campaign that has been conducted now for many years. And for instance, this is the ones that Ian Cameron had talked about in an earlier WOSMIP remote talk. You move an entire IMS type system into the field in a container like the TXL. So there are pros and cons with this, of course. The field sampling technique is lightweight and simple. You can move it around in a very flexible way, short installation time. You have also a well-known ambient detector background because you're measuring in the lab. And that is a problem I will come back to a little bit later. You can do plume hunting. The drawbacks is, of course, you have a long process time because you have the sample transport time included in the process time. That will lower your sensitivity, Radioxenon the case. You have sample transport logistics, costs money and time, and it's labor intensive, and there are risks for operational mistakes. The TXL type measurements have a higher measurement sensitivity, less manual operation when you have installed it. There's some work, of course, to install it takes some time, but after that, it will run. And you also here know the ambient detector background, but you need more power, heavier equipment, and so on. And you don't do any plume hunting. So the array project we are running at FY involves then the basic part of that is the cubes, which are smaller Radioxenon systems that are part of this Radioxenon array. An array is supposed to consist of maybe 5 systems placed out with some distance. These systems are quite small. The weight is below 400 kilos. They can be transported in one piece. And then it's a mini noble gas system in a way, although it's just a measurement unit for the array. But it still performs everything, sampling, processing, and measurement in one go. The power consumption is very, very small. I mean, it's like 1.5 kilowatts, something like that. My toaster at home, for instance, is more, I think. It's calibrated at factory. It's a simple installation. You connect the power, nitrogen, internet, if you want to use the internet, and then you press the start. So compared to the field sampling, most of the drawbacks you can strike out. The process time is shortened, no sample transport logistics, not as much labor, and less risk for operational mistakes. But still requires some power, but not very much. It's still lightweight. I would call it lightweight still. You can move around in a truck, and a short installation time. And you can still do the plume hunting. One slight drawback is that you don't know the detector background because that can vary from place to place. And how do you handle that then? To the left here, I just show a picture of different detector backgrounds from 3 cubes. 2 of them are located at the same place. The dark orange and green are located at one place, and the blue is located on another place. And you can see that you have a slightly different detector background here. And that is mainly because of potassium-40 in the construction material in the buildings, I would say, that causes this. It's different also when you go outside and so on. You can even imagine that you want to maybe move around with a truck and measure while you're moving. How do you handle then the detector background? Well, you can, of course, if you're in one place, you can measure later. But that takes time. Ideally, you want to measure for maybe 3 days at least. Or you can use a standard background. That's probably okay for stronger samples because standard detector background will not have a big impact on the activity concentrations you measure. But you can also treat the detector background using different analysis techniques compared to today. The way we do it now in the net count calculation techniques, we are subtracting a number in an ROI. You can do it differently to fit to a background shape instead. You can maybe assume a shape and then you can just tweak it for different locations. Or you don't use it at all. Use peak fitting instead and just assume some background shape. And it's difficult, And but we think there are ways to do this, and we are working on that right now at FOI. So here I just wanted to show you a picture of what's going on right now when we're testing the cubes. We are actually right now at FOI running 4 noble gas systems at the same time, like an intercomparison experiment actually. And there are 3 different types of systems, different generations or different kinds of systems. It's kind of interesting, I think. This one Sona 2 system, which is the IMS type system we are running at FOI, operating for IMS. We have the Sona 3 prototype that's running also at FOI right now, which is a new generation system. And we have 2 cubes, and they're all sampling the same air, and they are synchronized. And to the left, you can see the data is kind of a messy plot, but you can see the data for all 4 systems. They're plotted at the same time, and the agreement within error bars I think is great. They are all, the systems agree with the measurements agree with each other. You can see the small green dots, that's the Sona 3 system, which has a shorter collection time, and that will give rise to some peaks, sharper peaks. So this is actually not a disagreement, it's just that the peaks is sharper. And to the right, you see the sensitivity of the systems, that's the critical limit for the different systems. And as you can see, the Sona 3 is by far the best. It's not a surprise because it collects much more air and so on. And then we have the Sona 2 system, which is now operating in IMS for many years. And then we have the cubes, which have a slightly higher measurement sensitivity. But as you've seen, the systems are smaller and so on. That's the price you pay for that. But still, I think it's comparable to the Sona 2 system, actually. So I will stop by saying that I think that the measurement units we have developed for the array, they are suitable for ground-based mobile measurements. And I think this could be a faster and simpler way to map the global Radioxenon background, actually. And we can also use these measurements as an alternative to or independent verification of the stack measurements. And we are working on several different options to how to handle the varying site background in the detector. So thank you. And if you have any questions, I'm happy to answer.
Thank you, Anders. I have a question. Could you comment on the usability or the appropriateness of using this kind of measurement system for the IMS proper?
Well, I think that you should not view a cube unit as a measurement system of the IMS type. It's a measurement unit which is a part of a bigger system, which is the array, and they should not replace an IMS type system in that way, I think. So those are different things. Then it's better to use a Sona 3 system, actually, which is then for that purpose more, I think.
Okay, thank you.
Yeah.
Okay, Judah, do you have a question?
Yes, I got one quick question. In the 4 systems that you're currently running, what's the time resolution for the systems? How long is the sampling time for the Sona 3, Sona 2, and the Cube? Okay,
so the sampling time for the Sona 3 is 6 hours. And for both the Sona 2 and the Cubes, it's 12 hours, actually. So they are quite similar in that respect.
Well, thanks a lot, Anders. It's a great presentation. Thank you for staying up late in Stockholm to do this. I guess it's still light out there, but and thanks everybody. We'll see you for the next WOSMIP remote. Stay safe, and we'll see you soon.